Thank you. So I'm actually going to be talking about biomimicry in architecture. I'm not quite sure why it was listed as biomimicry in society, but the two are connected. And in actual fact, in the second edition of my book, I have tried to make much more explicit the connections between biomimicry and people and why it's important. And I must say it's been a real pleasure talking to most of you. I think I've spoken to lots of you over the last few days. And it's also very nice and very flattering to hear that most of you have seen my TED Talk. And then quite a few people said they'd seen my CE100 talk as well. And then I thought, well, my God, what am I going to talk about then? You're not going to want to hear the same old crap. So I deliberately didn't complete my talk until lunchtime. And so what I'm going to be talking about is some new projects, and I'm going to be offering some new reflections on old projects. And I'm also going to be talking quite a bit about new digital design tools that we've been using at Exploration. So when I updated my book, I thought in the introduction I would perhaps address some of the skeptics who are slightly critical of biomimicry. And there is one academic who wrote an essay called Biomimicry versus Humanism, in which he asserted that biomimicry is the opposite of humanism, and that humans are capable of invention ab origine, without precedent, whereas nature doesn't really invent. It's evolved based on sort of tinkering. It's improved on things steadily. And so what you see in nature is sometimes some curious starting points that have been highly refined over time. But I think that academic has actually missed the point, because I don't think it's a question of thesis or antithesis. I think biomimicry is a synthesis of the 3.8 billion years of research and development that we've inherited, together with the best that human ingenuity can deliver. And that's a pretty powerful combination. And this example is one that I sometimes use when people are slightly skeptical. I know very few of you are going to be skeptical, but I thought you'd be interested in these arguments. So, some people say, well, nature's all right, but it hasn't produced a jumbo jet or high-speed rotating axles and so on. But the fact is that it's solved many of the equivalent challenges in much more interesting ways. And this wood wasp, it has, at the end of its abdomen, it has an ovipositor, and this can drill into wood. So how can it drill without something that rotates? Because things that rotate are pretty difficult in biology. And the way it has solved this is with an ovipositor that is made in two semicircular halves, which is the magnified view you can see on the right there. And those can move back and forth like that. So the wood wasp pushes this into a crack in the wood, and then the ridges on the sides, those kind of grip onto the wood, and then it can push the other one in. It actually sort of pulls its way into the wood. And by doing that, it can drill about 3 or 4 centimeters into the wood without any rotation at all. And this was the source of inspiration for a new medical probe that can be used in very delicate situations, like drilling into a skull. And the great thing about it is it needs virtually no pushing force at all. It kind of pulls its way in, and because it's in 2 halves, it can follow a curved path. So by following a solution in biology, it's actually resulted in a superior product, which I dare say humans would not have thought of without that existing. And this is just a glimpse of the exhibition that we had in London. We were invited by the Architecture Foundation to put on a solo exhibition, which was very nice. And we played about with 3D printing and with digital design tools that were based on bones and trees. So this is using the SKO software developed by Klaus Matek, who's really spent his whole life studying the way that trees and bones grow. And then we combine that with an algorithm that we developed ourselves based on giant Amazon water lilies so that we could create a very rigid surface with a minimum of material. And you can see that some of the plinths at the end are solid there. And if you look at that in sort of volume terms, the 3D printed tables occupy 1/1000th of the volume of the solid ones. And that gives a sense of what we could achieve in terms of resource efficiency if we could really get closer to the way that biology has evolved structures. And I know I've used this example before, but this is, I think, a really good example of how much biomimicry can offer, particularly to architects. So this is abalone, and shells were probably one of the earliest examples of biomimicry. We know that architects like Filippo Brunelleschi, when he designed the dome in Florence over the cathedral, He studied bird shells and seashells. But you see, the massive advantage we've got now is vastly superior scientific knowledge. So if we look at an abalone shell under a scanning electron microscope, we can see that it's made up out of these layers of calcium carbonate, which are connected together with a flexible protein. And it gives it amazing resistance to crack propagation. So at a chemical level, that is 95% identical to ordinary blackboard chalk, but because of the microstructure, it achieves 3,000 times the toughness. And we developed a project recently. It's a house project. Is this film going to start? I hope so. So this... Yeah. Okay, it was supposed to start automatically. Did it? That's weird, because I tested it before and it was working fine. Let's try once more. It's not happy, is it? No. Okay, well, that's a shame. So in that case, I'm going to move on to talking about the Biomimetic office building, which I have spoken about quite a bit before, so I'll say different things about it this time. And I think one of the really key things about this project was the working method. So we insisted with the client that we had to, if we're going to make a breakthrough, we had to follow a different way of doing things. And we said that what we needed to do is to do a concept study first with a minimum of constraints, so no site, a minimal brief, no cost plan at the beginning. And we also needed a really excellent team. And so he had allowed us to select the team ourselves. So, sometimes I have experienced clients who insist on appointing their own team. There was one project I worked on where the structural engineer was appointed simply because he shared a racehorse with the developer. And the structural engineer used about twice as much concrete as a decent structural engineer would use. But anyway, this time we selected our own team. We had an excellent team, including some of the best consultants that I've got to know over the last 30 years, and a biologist. And I think what is required to get the best out of a team like that is a different approach for an architect. You know, there are the so-called iconic architects who the way they work is they tend to do a sort of sexy sketch, and then they expect the rest of the team to just make it happen. And if we're to get the best results, I think we need a bit of sort of architect's ego suppression. And I really like the way Benjamin Zander, in his TED Talks, talks about the way that a conductor works. And he says that the conductor relies for his or her power on making other people powerful. They may not make a sound at all. What their job is to draw together the best elements from the group and to unify that. And so in many ways, I think the architect's role is similar to that. So you need to draw the best out of the group, and then your job is to integrate that into a really unified whole. And it was interesting that some of the consultants involved, they'd been sort of harboring juicy little ideas for the last 20 years, and they'd never managed to get those implemented in projects because of the architect's ego. And the thing that really drove the architectural form on this project was daylight. We probably looked at, I'd say, about 30 different examples of light being gathered and distributed in biology. And I'm just going to show two of those. One is the fantastic spook fish. Now, the spook fish has a transparent head, and it has what are called diverticular eyes. So part of these eyes points upwards to the ocean surface, and then there's a part here which points downwards. And that's picking up very low levels of bioluminescence coming up from the ocean. And that has a mirror structure in its eyes. I think it is the only fish that has this kind of mirror. And that mirror can focus the very low levels of bioluminescence coming up from the ocean and onto its retina. And that gave us the idea for a large-scale mirror, which I'll show you in a minute. And then the other one I was going to talk about, I'm going to talk about, is called Anthurium warraquinum. So this is a plant that lives at the rainforest floor where light levels are incredibly low. And it's got lenses over its leaves, and somehow those are able to focus diffuse light. And this is the way we played with the lights. Looking at the building in section, what we found was that it was easy enough to get enough light to the top parts of the building. The challenge was how to get the light further down. And so we looked at the possibilities of harvesting light near the top and focusing that into fiber optic tubes. And that's why we looked at Anthurium weraquinum, which has these lenses, and somehow they are able to focus diffuse light. There are products around that can focus direct light, but this would be much more useful if we could master this. So this is going to become a research project. And what we concluded was that there was a really good case for shaping the building to let more light coming down into the atrium. And then we had the idea of a large-scale light reflector based on the spook fish that would bounce light deeper into the lower parts of the building. And then, biology normally makes dual use of structures, or often does. And so we thought about what we could do underneath that. And we thought that was a great opportunity to create a dramatic meeting space that would add value to the building. And what we see here is two quite different uses of biomimicry. So in one case, the spook fish, it's just a straightforward translation of an idea of a mirror into a building. It's pretty straightforward. The other is a much more complex approach, where we really will need to work in quite some depth with specialist scientists to understand how it delivers that function and how to translate that into buildings. And I sometimes find architects who think that simple ideas can't be any good. If it's going to be any good as an idea, then it's got to be really complicated, and you've got to be able to talk about it in really complex terms, and so you sound really clever as an architect. But I think that's nonsense. What we should be talking about is effectiveness, and both of these, I think, have the potential to be very effective. And now looking at the structure, the strategic form of that building was almost entirely driven by daylight. So the way we used biomimicry with the structure was to try and reduce the amount of material as far as possible. And we started looking at very efficient structures in biology, such as bird skulls. That's what I'm sketching here. And in bird skulls, what you see is layers of incredibly thin bony material connected together with struts and ties. So it's like a combination of dome technology and space frame technology, all in a humble garden bird. And it's an example of a very complex structure that achieves its efficiency by putting the material exactly where it wants to be. And then another one we looked at is the bone in a cuttlefish, which is similar. So it's similar in the sense that it's quite a complex structure. In this case, it has thin plates of bone which are connected together by these undulating walls. So what we did then was that we analyzed a fairly generic slab and column arrangement for this building. And we analyzed it in terms of which bits were working hard and which bits were structurally redundant. And all the bits that I'm shading in dark here, these are the bits that are not doing anything structurally. And so if we were to do what biology would do, which is to follow the shape that it wants to be, it would probably look something like this. We would have deeper floor plates in the middle where the bending moment is highest. We would have hollow columns because the stuff in the middle is not doing anything. And then we would take out some of that surplus material with void formers, like these BubbleTech bubbles. And this is only a fairly small departure from existing technology. In this case, fabric formwork, and the one below was bubble deck technology. And so we were actually getting reasonably close to the ideal that we identified at the beginning. And I think this is why biomimicry is, or can be, such a powerful design tool. Because in the design conversation, you can, with your biologists and your engineers and your collaborators, you can allow the conversation to wander off in pursuit of the most idealized solutions. And then having identified the ideal, you can come back to something that is achievable within the constraints within which you have to work. The constraints of time, technology, and money. I take the view that you should never start with reality, because that's a compromise. You should start with the absolute ideal and compromise as little as necessary. And I'm choosing my words quite carefully there. I'm not saying compromise as little as possible. That's the province of the prima donna. I'm talking about compromising as little as necessary. And that's what you need to do if you're to really deliver innovation, I believe. And this is how the building looks. So that form is driven entirely by daylight. That's the Spook Fish light reflector in the middle. And this is another exercise we did alongside the biomimetic sort of analog design, I guess you could call it. This was using genetic algorithms. So with this software, you can put a model of the surrounding site into the computer, and then you put in your constraints. So your constraints of, say, minimum floor-to-floor height, minimum light levels, maximum distance to fire escape stairs. We also set maximum surface area to volume ratio, because that has a big bearing on the cost of the building. And then what the software does is it generates thousands of variations and mutations, and it tests those against the parameters. And then it goes through a sort of extinction phase where it kills off all but the best solutions, and then it re-multiplies those. And it goes through that several times, and what you end up with is a solution that is highly optimized according to quite a complex set of parameters. And in that sense, I think it's getting very close to the process of evolution. The advantage here is that you can do this in sort of half a day on a computer. You don't have to wait a couple of billion years, which not many clients would tolerate. One more detailed aspect of this project, we were trying to find breakthroughs in every part of it. And for the glazing, we had a fantastic glazing specialist who was very into biomimicry. And he said, okay, well, why don't we learn a few tricks from curved leaves and shell forms where just by introducing a curve, you can make an element much stiffer. And conventionally, curved glass used to be very expensive because you would have to heat it up and then slump it over a mold. But now you can make what's called cold bent glass with toughened glass, very, very thin. It's made out of 2 layers of 0.9 millimeter glass. And that just assumes its own curve. And then by putting 2 curves together and connecting them at the ends, that forms a very stiff unit which can span from floor to floor. And this should achieve a roughly 50% saving in glass, but the biggest saving actually comes from designing out the aluminium sections, the mullion sections. So designing out that aluminium reduces the embodied energy of this assembly by about 95%. And that's a little sketch that shows that. So compared to a conventional glass build-up, it's using much thinner glass, and it's still perfectly strong. And that's how the atrium would look. So that's the Spook Fish auditorium in the middle. And one of the engineers involved has predicted that if this gets built, it should be one of the lowest energy office buildings in the world. So we're still working with the client, trying to find an end user for this. If you happen to know anyone who needs an office building, do come and find me over a drink. And we did some basic calculations on this, because we had a hunch that actually people talk a bit too much about the cost of, or the value of energy savings, when really we should be talking about the benefit of increasing human productivity. And there are plenty of studies now showing that you can, with the right internal environment, you can increase people's productivity by 10 or even 20%. So let's say this building was going to cost 90 million Swiss francs. And let's say there are 3,000 people in the building on a salary of 100,000 Swiss francs a year. That means the annual salary bill is 300 million Swiss francs. If you can achieve a 10% increase in productivity, that's worth 30 million Swiss francs a year. So the building would completely pay for itself in just 3 years. Unfortunately, that's what a lot of clients, that's the reaction of a lot of clients when you say that. So they think, well, that's quite amusing. But I do believe the debate is moving on. You know, people that own companies, they're thinking much more about the value of their staff, about how to attract the right staff and retain them. And we know from several surveys that have been conducted with large numbers of millennials that their choice of company and working environment is a much bigger factor now than it used to be 10 or 20 years ago. Okay, so now moving on to a project called the Mountain Data Center. So this is a new concept for an ultra low energy data center. And you might think, well, what on earth could biology teach us about data centers? And that's where it's important to remember that it's very much a functional discipline. So if you look at one of the key functional challenges with data centers, is how to keep the damn thing cool. So if you have a server in a building or a data center in a city, a very large amount of the energy just goes to keeping the thing cool. So the first move here was to locate the data center that's somewhere already very cold. In this case, a mountain in Norway that's been carved out for marble mining, and it has 90 kilometers of tunnels that are all at a steady temperature of 5 degrees C. So then it's just a matter of drawing that cool air through the data center in the most efficient way. And we started looking at efficient flow networks in biology. And it seems that most branching systems in biology follow Murray's law, a mathematical constant which governs the diameters of the parent and the daughter vessels. There also seems to be quite a constant angle at which the branching occurs, and there's a certain finessing to those junctions. So this appears to be an evolved minimum energy solution. And rather than arranging the data blocks in long rows, which would have meant you'd have long lengths of ductwork and a lot of bends in that ductwork, we gathered them in circular clusters, and then we designed that extract system using Murray's law. And that might look quite wacky and biological, but it's not that way just because we like biological forms. It's that way because we've identified a theoretically perfect solution, and we're trying to get as close as possible to that. And this project does have a bit of a sort of James Bond quality to it. This is the showcase server in the central cavern. So to get into this, you would have to go through a laser scanner for security. You go down this long tunnel. You get into an underground boat, and it arrives at the central cavern. And then there'll be a shaft cut up through the mountain to a disused quarry to take away the waste heat. And the client wants to make a little mini version of the Eden project, and he can be waiting up there with his white cat saying, "I've been expecting you, Mr. Bond." Sadly, this project is not going ahead at the moment because the client made a bit of a mistake with his business plan. The people that own the mountain, he invited them to meet one of his potential clients, which was some massive data company in Northern Ireland. And this data company sent a private jet over to Norway to pick them up. And of course, the owners of the mountain saw how much money these guys had and how profitable it was, and the sort of dollar signs were going up in their eyes. And they decided they wanted a rental value for the inside of this mountain that was almost as much as office space in the center of Oslo. So never mind, onwards and upwards. We're still working with that client, trying to find an alternative location. So now from the glamour of James Bond to something a whole lot less glamorous. This is a water treatment facility, and we were asked to get involved with a tender that was going ahead in the Middle East. It was going to be a massive new water facility. And interestingly, this tender was going to be judged partly on construction cost, but also on 10 years of running cost. And that's actually a really good clause because it provides a very strong incentive to design it in a low energy way. And when they showed us one of their existing facilities, I must admit, I thought that was a pretty rubbish layout because it's very rectilinear. There's a lot of space between the elements. And an engineer that I work with quite a lot, he said, well, isn't that incredibly arrogant of you to think that you as an architect, you could improve on something that engineers have been working on for decades? And I said, well, no, I don't think it's about being arrogant. It's just about being curious. And even if we could only make a 2% saving in the energy, that would be worth having. It would make the tender more competitive. So I decided to get one of the fantastic boffins in my company to develop a little algorithm based on Murray's law. And this shows how the algorithm works. This is a hypothetical layout. So the white circles are bits of equipment, and then the straight lines are the things that connect them, the pipes. And what the algorithm does is it works out the optimum relative positioning of these, and also the optimum angle. And if you look at the figure down here, that's the total length of pipework from a starting point of 100. So that was one. That came down to 64%. And then this is a slightly different layout, which optimizes in a different way. So keep an eye on that figure. So both of these achieved really pretty significant savings. And interestingly, they ended up looking quite biological. But again, it's not just because we like biology, it's because we've identified the principles and let that determine the layout. And then my grumpy engineer colleagues sort of said, well, I suppose that's worth doing. I decided to get a different engineer involved to take it a bit further. So in this one, we actually worked with an absolutely realistic sequence of elements for a water treatment facility. And now we also factored in the friction effect of the bends. You can work that out in terms of effective length. It's well known what a 45-degree or a 90-degree angle does in terms of effective length. And so we've got a figure here for total equivalent length. So that combines pipe length and optimized angle. And you can see that came down to about 38%. So I'd say that was a pretty good result. Unfortunately, the tender was cancelled, so we didn't get a chance to implement this. Never mind, onwards and upwards. So now the Zero Waste Textiles Factory, and we worked on this one with Dana. So we had a fantastic team. We had Dana, and we also had a wonderful green chemist and a really good water expert. And a really good client in many ways. He had a vision for what he wanted. He wanted a completely new paradigm for industrial buildings in India. And he wanted this to be a wonderful working environment for the staff. He wanted it to be as close as possible to zero carbon and closed loop on water and close to zero waste. And so we worked out quite a detailed water strategy. Textiles factories use colossal amounts of water and energy, and that's what a conventional approach would look like. And by designing out some of the toxic inputs, the dyes and so on, we were able to use biological forms of treatment which offered the potential to get very close to closed loop on water. And then with the solid waste, that's what a standard factory looks like without waste minimization strategies. So only about 40% of the raw cotton ends up in the yarn. The rest ends up as forms of waste. But we actually managed with the client, they'd done quite a bit of this already, we managed to turn nearly all of those into other saleable products. So the shorter fibers went to make lower quality cloths. Some of the stuff was used to make insulation products. Some of it was used to feed a biomass boiler. And the main thing we were looking at here was ecosystem models. So looking at how we can connect up bits of the system to deliver efficiency savings. And we conceived of the scheme as having three main realms. There was the factory with all the equipment, there was an energy cycle, and then there was a water cycle. And the main move with the energy cycle was shifting it from coal to biomass. So we were getting heat and electricity. We were able to reuse a lot of the waste heat on the input here. Some of the solid waste that couldn't be used for anything else also went to the biomass. The food waste from the canteen went to produce anaerobic digested gas. The fly ash went to cement replacement. The waste from the compost went to the biomass production. And then the water cycle looked like that. There were still some things that were problematic. It's very difficult to deal with bleach in a benign way. But our client said that the market just isn't ready for unbleached cotton. I'm not convinced personally, but anyway. And this is how the interior of the factory looked. So the whole working environment would be full of natural light. They'd have views out to the sides. And you can see that it's actually a very deep span. So that's about 40 meters from side to side. And in order to refine the structure, we looked at ideas of hierarchical structures in biology. So to explain that, let's just imagine you've got a structural element which is a square section, solid. If you make that a round section, that comes down to 82% of the material. If you make it hollow, it comes down to 20%. The next stage is you can optimize the shape, so it's thickest in the middle where the forces are highest. Then you can add the first layer of hierarchy, where you turn it into a kind of truss. That comes down to about 5% of the material. And then each of those elements you can turn into a truss, and it looks like roughly like that. So that's down to 2%. So that's 2 layers of hierarchy. And in theory, you can keep on going. And when you look at that last one, I know what you're thinking. You're thinking that looks just like the Venus flower basket glass sponge. And you'd be right. 8 levels of hierarchy, all made with locally available materials at benign temperatures. And that's what we can do. So that was a study looking at how we could turn that truss into a hierarchical truss, which would use more human input in terms of design and labor, and much less physical input. In a country like India, where there's an abundance of people, but physical resources are quite expensive, there's a very good case for that. So this is how the scheme looked. And we delivered everything that the client wanted. It was zero carbon, close to zero waste, closed loop, nearly closed loop on water. And his finance guys said, so what's the payback period? And we said, well, it's 6 years. It's pretty good, isn't it? No, the economic conditions for this aren't quite right, are they? And we said, oh my God. Well, maybe we need to sort of broaden this. And I think this shows how when you run into problems, maybe you need to collaborate more widely. So we said, just supposing the factory we'd completed the factory, and on day one you brought around one of your best clients. Say it was the international buyer for H&M, and on the basis of what they saw, if they were to give you an average sized contract, what would that be worth? And they said, the profit from that would pay for the whole building 3 times over. And we said, well, why aren't you prepared to go for it then? And they said, well, we're not convinced that's real. So that was a bit frustrating. But we're still working with the client, and he says he's completely committed to building it in a couple of years' time. And we've treated that as an opportunity, actually. So now we've done a research study looking at how we could work with the machinery manufacturers. Those machines have a very long lead-in time. So we're taking advantage of this 2 to 3 year delay to try and find additional savings in the overall energy picture. And moving on to the Sahara Forest Project now, I've talked about this project a lot, so I'm just going to talk about some aspects of it that maybe you haven't heard of before. And for those of you who aren't familiar with this, it was inspired by the Namibian fog-basking beetle. It's a project for arid regions, hot arid regions, and it's a model for how we could create zero-carbon food in some of the most water-stressed parts of the planet, as well as generating renewable energy and revegetating deserts. And that's where we were with the project about 6 or 7 years ago. And I think every ambitious project needs a stroke of luck. And we had a bit of luck in that we hooked up with a Norwegian organization who brought with them quite amazing funding and political connections. And one of the first things we said to our new Viking friends was, we're very pleased with the project. We're confident about what it can do, but we don't feel as though we've got it in front of the right people yet. And a few months later, they heard that the King of Jordan was on a state visit to Norway, and they managed to get a meeting with him. And he had with him one of his ministers whose genuine job title was the Minister for Mega Projects. And they both loved it. And we thought, okay, now we're getting it in front of the right people. So that led on to feasibility studies in Jordan and Qatar, and we built a version of this that was built in Qatar. It was opened by the Emir during the climate change talks in 2012, and it produced cucumbers with half the amount of fresh water of conventional approaches throughout the summer. And the thing that we've really pushed on this is ecosystem models, looking at how we can get a whole cluster of technologies to work together so that the output from one becomes the input for something else. So we've got the seawater-cooled greenhouse here. We've got concentrated solar power. Those are halophytes, which are crops that can grow directly in seawater. We've got algae. That's some conventional desalination, which can increase the productivity of the greenhouse. The greenhouse does produce fresh water. These are evaporator hedges. These are conventional crops. This is salt processing, and this is biochar. And in principle, we're using what we have a lot of, sunlight, seawater, and carbon dioxide, to produce more of what we need: biomass, oxygen, electricity, crops, and materials. Everything runs on current solar energy. Seawater is a major input. Carbon dioxide is absorbed in a number of locations. And then, unfortunately, I don't have time to go through all these interconnections, but it's a very densely interconnected system that moves towards being zero waste and highly productive. And these are the kind of things you get out of this: biomass, oxygen, energy for export, crops, and even building materials. And in my book, in the second edition of my book, I talk quite a lot about some of the academics who are applying deeper principles of biomimicry to these kind of models. They're commonly known as eco-industrial parks. I'm sure you've heard of Kalundborg and so on. But now academics are moving beyond a sort of metaphorical approach and actually looking much more closely at the characteristics of eco-industrial parks and real ecosystems and seeing what the differences are and how we might be able to refine those eco-industrial parks to perform even more like real ecosystems. Some people, when they look at these kind of models, they say, my God, that looks hellishly complicated. How are you going to deal with that? And we've been developing some design tools that allow us to do this. So this allows you to connect up technologies and connect up the inputs and outputs. And it shows you at every stage what is underutilized in that system and how you can add stuff to that system to take advantage of waste. And then you can run the system and you can see exactly how it's performing and what it's producing. You can even cut some of those links to test the resilience. If you cut one link and the whole system goes into chaos, then you know that it's not a resilient system and you need to add greater redundancy and diversity to it. And another thing you sometimes find is with these complex models, when you run into difficulties, it's often a lot of pressure to go back to something much more conventional. People start saying, oh my God, this sounds awfully complicated. Can't we just do something a bit more ordinary? And halfway through the Qatar study, we had a rather disastrous meeting with a client when they were having a sort of attack of the doubts, and there were all sorts of things they were worried about, and this was one of them. They said, you're going to have a real problem with your sea pipe, because it'll scale up and it'll get clogged up with biofouling. And they said they have to put masses of bleach down their pipes to keep them clean, which is just a nightmare. And we thought, well, there must be a better way of doing things. And biology is pretty good at controlling scale formation in beneficial ways. So the idea we had was, wouldn't it be great if we could get that scale to form where we wanted it to and not where we don't? And I really like this quote from Ben Okri, because I think this captures what you need to do. He said that adversity is not the end of a story, but where there is courage and vision, the beginning of a new one, a greater one than before. And what I mean by that is when you run into these difficulties, you need to try and apply the same level of ingenuity to solving those problems to ultimately produce a richer scheme. And in this case, we turned to a technology that's called BioRock. And this, at its simplest, involves just putting a steel frame in seawater, passing a very low-level electrical current through it, perfectly safe for wildlife. And then you get electrodeposition of minerals, calcium carbonate and magnesium hydroxide. And after a year or two, it looks like that. It can be stronger than reinforced concrete. And our idea was to create lightweight wire frames that we would put at the start of the sea pipe so that that would take out the excess scale, and the water downstream within the pipe would be slightly more acidic, so that would prevent scale formation on the pipe. And it turned out that this even produced very small amounts of chlorine, so that dealt with the biofouling problem as well. And after, say, a year or two, we could pull out those frames. They would have grown into structural elements, and we could use that for our project. And there's something very elegant about being able to grow materials in the pipe that is supplying the project to expand the project. And now we're just about to build in Jordan. So this is the Red Sea, and this is the Arava Valley here. Absolutely perfect climatic conditions, and I would argue also ideal political conditions. Jordan is one of the most water-poor countries in the world. It imports quite a lot of its food, it imports 95% of its energy, and it's got a growing population, which has recently been swollen by an influx of war refugees. So although we think of Jordan as a haven of peace surrounded by some quite tricky neighbors, it's actually a very precarious situation. It'd be very easy for that whole thing to unravel and descend into resource-based conflict. So we're hoping that if our scheme really takes off, then it could make a significant contribution to food, water, and energy security. And to draw together some conclusions now, obviously we're in a really weird situation with the events earlier in the week, and it reminded me of after Obama was elected. You know, a lot of people were saying, wow, he's the green leader we've been waiting for. And then a few years later, people were starting to get a bit frustrated. You know, he hadn't managed to do much. And Hazel Henderson came out with, I thought, a very apposite comment. She said, we need to give up on this idea of waiting for a green leader and consider this. We are the leaders we've been waiting for. All of us, you in this room, me, collaborating together to lead. And I think one of the most exciting things about biomimicry is that it has the potential to draw out fantastic success stories that previously just lay hidden in academic books, read by very few people. And we need scientists to reveal nature's secrets, to report on the health of the planet, and in some cases to create justifiable fear about the future. But as designers and business people, I think we have a different role. Rather than creating fear about the future is something we should fearlessly create. And creating the future, a positive future, is not as strange as it might sound. Yes, you can let the future happen to you if you want to, or you can choose to shape it. And if that's what you choose, then that's what you're doing all the time. Moment to moment to moment, you're shaping the future in the decisions you make, the actions you take. So should we be optimists or pessimists? Well, I agree with Hans Rosling. We should be neither, because both of those positions imply some sort of sense of inevitability about the future. What we should be, he says, is serious possibilists. We should decide on the future we want, and then we should set about creating it with inspired collaboration. Thank you.